The following program is brought to you by Caltech.
Good evening. I'm Ken Farley. I'm the chair of the Division of Geological and Planetary Sciences here at Caltech. Before we get started with tonight's lecture, I want to tell you about what's coming up next month so you're well prepared. So on April 27th, Mary Kennedy is going to give a talk entitled Neuroplasticity. What is it and what can it do for you? I have no idea what the answers to those questions are, so I guess I better come. So for tonight, our speaker is Professor Jennifer Jackson. Jennifer is an assistant professor of mineral physics in the GPS division here. And she was hired into the seismological laboratory something like 5 or 6 years ago. And you might wonder a little bit why a mineral physicist is hired into the seismological laboratory, which is part of the, of the GPS operation. And I want to say something about that because it gives you some context for what Jennifer does. So I'm sure all of you are aware that one of the major functions of the seismological laboratory is monitoring and reporting on earthquakes both locally and globally. If you live around here, you cannot have missed the reporting function with the media parked on Wilson for several weeks. It was quite the circus over there. So earthquake monitoring and reporting is a central function of the seismological laboratory, as is characterizing earthquakes themselves, how earthquakes work, how faults rupture, that sort of stuff. But there's a whole other aspect of the science that the seismological laboratory is interested in, and that is characterizing the Earth's deep interior. And the linkage here to seismology is that one of the central tools by which one understands or characterizes the Earth's interior is with earthquake waves. This is the main way that the Earth's interior is illuminated. Earthquakes occur, they propagate energy through the Earth's interior, and that energy is detected in seismometers. But in order to interpret that information, we have to actually understand the way seismic waves are being transmitted through the Earth's interior. In other words, we need to know about the material properties of the minerals that occur in the Earth's interior. And that is a topic of mineral physics. So that's the linkage to Jennifer Jackson. She's interested in characterizing the minerals of the Earth's interior, both with respect to their seismic properties, but also their more fundamental properties that control the behavior of the Earth's interior, properties like thermal conductivity and density. So Jennifer is an experimentalist. She takes materials of appropriate composition up to very high pressures, she squeezes them to very high pressures and heats them up. And then her major tool for characterizing those charges is X-ray radiation produced in synchrotron laboratories. So with that introduction, Jennifer Jackson is going to talk about good vibrations inside the Earth.
Thank you very much, Ken, for that introduction. And I'm very happy to be here this evening to talk about the research that we're working on. And a lot of this is hot off the press. And I'd like to also acknowledge that this is a memorial lecture and thank the Watson Lecture Series for this opportunity. So now we're going to talk about good vibrations inside the Earth. And these vibrations are essential and fundamental properties to everyday materials. And everyday materials encompasses the naturally occurring substances that are made inside of the Earth or have crystallized since the beginning of the solar system. And those are vibrational properties, and those help us understand what's going on inside of the Earth and can help us provide a link to what we observe at the surface, such as volcanic eruptions and events that occur in the brittle regime, which are usually the earthquakes. And so first, I'd like to acknowledge my research group here. PhD students in the center here, we have the core of the experimental group, Dongzhao Zhang, Caitlin Murphy, Aaron Wolf, and June Wicks. And PhD student Dan Bauer, who focuses on geodynamics. Undergraduate student William Steinhardt, he's a senior, he's graduating very soon. And Dr. Bing Chen, he's a Texaco postdoc fellow. And some of the work that's presented today is the result of their hard work. I'd also like to acknowledge the National Science Foundation through a few different portions of the funding agency and the Keck Institute for Space Studies and California Institute of Technology. So let's go back 3.5 centuries to a very primitive view of the Earth's interior, where there's a red-hot ball of fire in the center of the Earth that delivers molten material up to the surface, and fictitious people are blowing wind out of their mouth to create the atmosphere. And this inspired several science fiction tales, including the Journey to the Center of the Earth that many of you are probably aware of by Jules Verne, where they journeyed into the Earth experiencing very improbable geographies, and it still inspired us to understand the real phenomena and activities that are happening inside of the Earth. And more recently, there was a Discovery Science Channel episode about a character named Dallas Campbell who was interested in physically going down inside of the Earth. So he himself wanted to journey to the core and wanted to figure out how to do that. And I'm just going to show a little video clip of me demonstrating that that is probably not possible. And I'm using some of the experimental devices that we use to show him that.
To simulate conditions at the Earth's core, Dr. Jackson placed a grain of salt in a special diamond anvil. She applied 10 bars of pressure, and the salt imploded. A bar is wrong.
It's the pressure that I feel at the surface of the Earth.
At the center of the Earth is how many bars?
4 megabars.
Mega meaning?
4 million times.
Okay, so I'm going to need something that's not made of salt.
Right.
Start with. What would physically sort of happen to me in my sort of fridge capsule type device?
Everything would collapse as you journey into the center of the Earth.
Completely, so I'd just be squished.
Completely squished.
I was totally despondent, and it wasn't like I could go somewhere else for another opinion. These
So now, instead of trying to physically go down there, we have some more modern tools to understand what's happening deep inside the Earth. Some of those modern tools have allowed us to explore the connection between the deep interior of the Earth and the surface. So first, I'd like to make that link. And that link is through, just one example here, is a very large igneous province, a very large volume of lava that was erupted about 65 million years ago. That happened at about the same time that the Chicxulub impact occurred. And that erupted, the original area was about 1.5 million kilometers squared. Now that has reduced to about 500,000 kilometers squared through erosion, but that's roughly, the original eruption area was roughly about half the size of India. And the release of volcanic gases, such as sulfur dioxide, had a fingerprint on the climate change. It was roughly about a couple degrees C in temperature at the surface, which produced major stresses on biodiversity. And here's a picture of these crystallized lava flows, which are called the Deccan Traps. Now, what is thought to be an origin, it's one hypothesis, is that this eruption was instigated by a deep-seated mantle plume. Now, that's one hypothesis, and that deep-seated mantle plume had to arise deep in the mantle. And the buoyancy of that plume, essentially the control of how fast that came up and whether it did come up and from what depth it came up and what it's made of, relies on our understanding of how these minerals behave at very high pressures and temperatures, because we cannot directly access those minerals. They are deep below what we can sample with our hands, and that's the next slide that I will go through. And we have had a drill core that has gone through the continental crust all the way down to about 12.26 kilometers, and that's the Kola borehole that's in Russia. And that was recently superseded by a drill core also in Russia in February of this year to roughly 12.8 kilometers in the continental crust. So the continental crust is easier to drill through than, for example, the oceanic crust, which is made of a denser rock called basalt. Now, that project, as instigated by Harry Hess, was called Project Mohole. They want to dig down into the boundary between the lithosphere and the mantle. And the first drill that went through was only a few hundred meters. And now, in the next decade, they want to go down to several kilometers. And they're proposing several sites to go down there. So if we take let's take the deepest drill core, that's 12.2 kilometers, and compare that to the radius of the Earth, which is 6,371 kilometers, roughly 4,000 miles. This is just a mere pinprick into Earth's interior. So how do we know what's deeper? So we have to rely on other sources of information. We can look to the sun. We can look at their spectrum of at the sun's spectrum of elements. And we also look at the mineralogy and geochemistry of primitive rocks in our solar systems, which are called chondrite meteorites. We also look at mineral packages that have been ripped up from the upper mantle, and these are called mantle xenoliths. These are these green nodules that are found, that you can see in this picture, in a matrix of basalt, and also inclusions of diamond. But those only take us to about 200 to 300 kilometers depth. So we're still only fractions of the way into Earth's interior. And if we want to understand how the interior of the Earth, especially our dynamic Earth, interacts with our surface, we need to understand what's happening down there. So we use other observations, such as a suite of geophysics observations, the seismic body waves that are generated after an earthquake occurs. That energy is released and propagates through the rock, and it propagates at a speed at which characterizes that rock that it's propagating through. However, we don't know what that rock is unless we have measurements of those wave velocities or the vibrational properties. So the vibrations inside the minerals that make up that rock control how the seismic wave passes through that region. And so the next set in our toolbox is a set of experiments that we can do under extreme conditions to determine these properties of the minerals under their conditions that they're existing inside of the Earth. And so we will focus on measuring these vibrational properties and trying to understand what lies beneath our feet. So in this figure, I want to show the radially averaged properties of the Earth's interior. So this is a model that seismologists have used, and one of the authors, Don Anderson, is here at Caltech, and this is called the Preliminary Reference Earth Model, and this describes just a radial average material properties of Earth's interior. So it describes the shear waves, their propagation into Earth's interior as a function of depth, and we see the absence of that shear wave in the outer core, which told us that the outer core is in the liquid state because it cannot withstand a shear wave deformation. And the P wave is the pressure wave, and we'll go through some of these in just a minute, and the density. So from these observations, the stratification of Earth becomes obvious, the general picture of what's inside of Earth's interior, but the dynamics aren't understood from this picture of the Earth. So through advances in seismic tomography and normal mode data, we're able to see variations in the wave speeds if we compare them to a reference state. And these variations tell us that the Earth is not simple as we go down into depths. It's probably as complicated, or at least more complicated than we thought, if we compare to the Earth's surface. And the red regions here are where the seismic waves travel slower than a reference state, and the blue are where they travel faster. So now one may ask, so what is causing those differences in wave speeds? And several years ago, it was thought that just temperature was causing it. So just heating up the material would cause these variations. But in fact, that's not the case. After some experiments were done, it was shown that temperature alone can't describe these variations. It's likely a combination of temperature and composition. But we still don't know what's the root of these variations until we do a measurement of candidate materials that could give us the information to describe the low velocities or high velocities that are seen in these images. So if we want to simplify the mineralogy of Earth's interior, simply from looking at these observations that we have on the surface, we have a rock, and we have a suite of rocks, and we can generalize the mineralogy and start at the upper mantle, which is a more simplified mineralogy. And we have a garnet peridotite rock, which has olivine, garnet, and pyroxene. And now these minerals will transform into higher pressure, what are called higher pressure polymorphs, that after the experiments were done to show that phenomena, they were shown to explain, at least in part, some of these seismic discontinuities that highlighted our stratification inside of the Earth. Now, as we go deeper, these minerals transform into yet higher polymorphs, higher pressure polymorphs. And what we're going to do is we're going to focus mostly on the lower mantle of the Earth and an iron-bearing oxide that displays very unusual characters due to its iron concentration. So let's take a minute to talk about how to generate these pressures that we need to generate to simulate the conditions inside of the Earth. If we look at half the way into the lower mantle, which is 500,000 times atmospheric pressure, that is equivalent to a Boeing 747 sitting on top of a high heel that's about 1 square centimeter. So many of us think that that would be a very uncomfortable situation. However, the minerals inside of the earth are very comfortable there. I mean, that is why they exist down there, is that they accommodate these pressures and inside of the earth, the temperatures. So now if we go down into the core, it is 3.6 million times what we're feeling at the surface. So this is, you could also put this in terms of gigapascals, which is 360 gigapascals, or 3.6 megabars, because of 1 bar is, of course, what we feel at the surface. So in order to generate pressures, we need either a very strong force or a small area or a combination of both of those, or some type of trade-off in order to generate these pressures. So what we use is a diamond anvil cell. It's a small compact device, or I brought several of them here, and different designs are used for different experimental probes. And this is an enlarged anvil, of course, but we essentially take very small anvils, which are about 1/4 carat, and oppose them, cut off the culet, and place the sample on the culet with a metal belt around it. This is also called a gasket. We use diamonds because of their hardness, their clarity. They are transparent to a wide range of electromagnetic radiation, so we can probe the minerals that are being squeezed in between these anvils by a suite of spectroscopic methods, be it light or X-rays. It has a high thermal conductivity and a high melting point. This is very helpful when we're trying to simulate the temperatures inside of the Earth so that the whole device does not break down. So here's a picture of the cells, and I welcome you to come up and look at them after the talk. So if we zoom in on the sample chamber area, it's a sample that oftentimes we synthesize here at Caltech, and some of those samples need to be the synthesis is very specialized, so we do that all here. And we place that sample inside of a pressure medium the goal is to have a very soft environment, as close to hydrostatic as possible, so we can simulate the conditions inside of the Earth. And we place a gasket around that sample, close the cell, and tighten the screws. So believe it or not, pressures of up to 3 to 4 megabars can be generated by these 2 Allen wrenches. So you can also see where we probe the sample with X-rays, and this is a simple scattering environment where the X-rays come out in the same direction as they come in. And we also have an infrared laser that is collinear with that probe so that we can heat the sample while we measure its properties. And here are a few pictures of samples from the microscope showing the very small size. This arrow is 1 millimeter, and different samples on top of the culet, and then the gasket is lowered down over, say, a nice single crystal of an oxide, representative of Earth's lower mantle. And then one has to ask, how do we know what pressure or depth this mineral is experiencing? So in some cases, we use a ruby that's placed right next to the sample, and the chromium inside of the ruby gets excited by a laser, and we measure that fluorescence as a function of, as we squeeze the pressure, or as we squeeze the cell, the volume around that ruby decreases, and the resulting signal from the ruby, as it's fluorescing, increases in wavelength in response to that volume change. So these changes in wavelength that are a result from me tightening the screws can be correlated with a pressure. And of course, then pressure can be correlated with the depth inside of the earth. So now we know what depth or pressure our mineral is experiencing, and we can keep it there. So that's the elegance of these cells, is that the properties that we're interested in, we can measure those at very controlled pressure or depth steps and temperature. And so now we need to measure those properties. So how are we going to measure those? On a very, very tiny, tiny sample. So we need these small samples because the anvils that we have are not infinitely large. So a small sample means a small signal, usually. So if we took a conventional source of X-rays, so we're going to focus mostly on X-rays, those are characterized by low brilliance. So in this plot here, the important things to note, it's a little bit fuzzy, is that the curves that are down below here are characterized conventional X-ray sources that can be found in a laboratory, say on campus here or other campuses. But in order to get about 10 magnitude higher in brilliance, which is the amount of photons per area, per time, per solid angle. So this tells me how many photons I can blast at my sample and how well I can focus that. So this is all very important for generating very high pressures in the cell and making a measurement that I can observe. And so these curves up here they characterize X radiation that's produced by synchrotrons. And those are national facilities that can be found around the United States. But the very bright ones, there's only 3 of them in the world. And one of those is at Argonne National Lab, the Advanced Photon Source. And so I make an analogy of just how bright these are by just showing a few specks in the same area compared to a packed area that would indicate just how many photons per area are being focused onto a sample at a national synchrotron source versus what can be focused on an in-house instrument. So in order for us to measure these vibrational properties that we're interested in for iron-bearing phases, we need to go to these national facilities. And the Advanced Photon Source is the one that we're doing most of these measurements at. So just so happens that it falls on the route, the mother road, Route 66, that connects Los Angeles here to Chicago. So how many people have traveled Route 66? Yes, great. Yes, I have too. And it's usually not for the experiments, though. Usually we fly there. It's a more efficient way of getting to the synchrotron. So we end up in Chicago, so we usually fly there. We prepare these experiments well in advance. We get a certain amount of what's called beam time, which is granted to us based on proposal system. And we prepare several weeks in advance, fly in with our group. We have backups. That's because we only get, let's say, 3 or 4 days, and we have to use these X-rays 24/7. So we want to make sure that we're using our time well, and we're making very good measurements. So here's an aerial view of what the Advanced Photon Source looks like. We see right here is the linear accelerator. That's the instrument that injects the electrons into a booster ring, which is underground here. And that starts the acceleration process. Now in this booster ring, they are then injected into the storage ring with an energy of about 7 giga electron volts. So they're kept in orbit and synchronized through a series of electromagnets. Now, each experiment is then placed on a tangent to this circle where the shutter, as soon as the shutter is open, the X-rays come down the tube, and they're characterized by a very broad spectrum of energies. And what we do is we slit down to a very small energy range in order for us to do our measurements. But that's the gist of the synchrotron at the Advanced Photon Source, which is the one of 3 largest sources that can produce such brilliant the most brilliant X-rays. And here are just some pictures of the group inside of different experimental hutches, mounting cells into the X-ray focus spot before the X-rays are on, of course, and monitoring some of the spectra that we've collected, and also monitoring some of the detectors, testing them and making sure that they're working properly. So now let's take a step back and discuss what are the questions that we're interested in understanding. So we're at the synchrotron, and I want to show briefly this cartoon of the cross-section of the Earth again. Now this highlights the region, this region right here is the Coremantle Boundary, which is about half the radius of the Earth, and it separates the silicate mantle above and the iron-rich core below. So it's the most drastic in terms of density differences across an interface. And it is, in fact, a very dynamic boundary. But we don't understand the detailed connection between this surface, this extreme boundary layer, and the surface of our Earth. So we've got 2 major surfaces in our planet that are linked, but we're still trying to understand those connections. So what I'm going to focus on right now is this region right here, which are called ultra-low velocity zones, which were observed by seismologists to have roughly 10 to 40% reductions in wave speeds, depending on the type of wave. So this is very unusual for the Earth. We might have maybe 0.5% or perhaps maybe 1% variation in wave speeds, but 10 to 40% is very unusual. So the hypothesis before suggested that there could be some melting down here, because this is at a very hot boundary layer. Perhaps the material could be close to its melting point, but it's been difficult in simulations to contain that melt so that these structures are really not very long-lived, or the melt just pools down or pools over the whole boundary layer, the whole surface of the core. But seismologists have observed patches that have some dimensionality, which means that they need to be sustained for some finite amount of time. So in order to understand these patches more, we need to have seismic wave velocity measurements, or their acoustic vibrations of candidate materials. Of course, we would also like to know the temperature of that boundary layer and how the phases interact with each other in terms of what is their equilibrium chemistry. So let's take a step back. This is a 2-dimensional, this is a linear chain of atoms that is going to be, I'm going to use that to describe vibrational properties in a 3-dimensional lattice. So every atom in a material is connected via a bond, and that bond is described, or can be described by a spring constant. And that spring constant controls the vibrational properties. So the stronger that spring constant is, then the stronger the material is, which will be reflected in their vibrational properties. So if we transmit a wave down this lattice, and it's propagating along the lattice chain, along the atomic plane, that's the longitudinal velocity or longitudinal vibration, or the P wave. Now, this is the same P wave that seismologists measure when they, after an earthquake, and they set up their stations. Now, when the vibrational motion is perpendicular to that pressure wave that's coming through, that's a shear wave. So that's also called the transverse wave. Now, crystals have many other sets of vibrational properties that describe perhaps how they bend in and out of the plane as a collection of atoms or as a group or as a molecule. So there's a whole suite of vibrational properties that describe a mineral. And we focus mostly on the P and S waves, but we'll also see how the other vibrations give us important information about the minerals. So let's take the structure. The structure is the one that we're going to be focusing on, is that the oxide, the magnesium iron oxide, which is found in Earth's lowermost mantle. And now, there were a lot of measurements done decades ago at very low pressures. And nothing unusual was found. It's thought to be kind of an average mineral. Just squeeze it, get stiffer, okay? But until there were very detailed measurements at much higher pressures, did we find out that this mineral undergoes some transformations that produce vibrational properties and density properties that we couldn't predict about a decade ago. So that's why this is an exciting mineral phase. Okay, so what are these vibrations? Or what can we say about different types of vibrations? We can draw a cartoon and see that for the iron-oxygen bond and the magnesium-oxygen bond, which will be depicted by this black spring, and the magnesium to oxygen bond connected to this blue spring, and that sort of depicts the range of motion, that the magnesium and oxygen have a higher frequency of vibration than the iron and oxygen bonds, just from measurements that have been done at low pressures, just to give an impression of what these different frequencies mean. So that's why I call them, and one more thing, so these vibrations are, what we can use to make the link between the seismic observations and the mineral chemistries and mineral phases. So that's why I call them good vibrations.
I'm picking up good vibrations. She's giving me the excitations. I'm picking up good vibrations.
So these good vibrations in the minerals, there really aren't any bad vibrations. They're all good. They inform us on, say, how fast a seismic wave or how slow that wave will go through the material. And if we know what material it is, then we can also determine how dense that material is. And that will come up later. So how do we do these measurements? We introduce an X-rays with a very specific energy that interacts with the lattice that is vibrating. So it interacts with these motions. And after that interaction, it is changed in energy. And that energy change is proportional to a specific vibration. So the low energy wavelength, or the low energy excitations, which are long wavelength, also called long wavelength, are the acoustic modes in our sample. And the higher frequency ones are, they contribute to other pieces of information, such as thermal conductivity or the thermal pressure of the material. And so if we take our measurement, which we can see in a schematic here, we scan around this energy, and we are then able to probe all of these different vibrational states. And in this energy diagram here, it just shows that if the state is the same, so a G0 to an E0, that's considered no energy exchange, and that's in the blue line here, also called the elastic scattering. And every other mode here is depicted away from this energy. It's also called an inelastic scattering process, but that is exactly what is being measured by the interaction of these vibrations. So if we can analyze that spectrum, then we can know what are the P and S waves of this material, in addition to many other thermodynamic properties. So if we take this example of an iron-rich oxide, so here's our oxide again, and we look at this let's look at the blue spectrum here. This was collected at room pressure as a function of energy. Let's relate that to the vibrational frequencies and what parts of the spectrum mean what. So the first part is where we obtain our seismic information. These are also corresponding to the black vibration depicted here. And the rest of the modes are the higher frequency modes, which are depicted by the green and the blue springs that are moving at moderate to faster frequencies, which collectively, so if we extend and we look at the whole spectrum, they give us the total thermodynamic information, and that can give us the thermal pressure, for example, or the thermal conductivity. But let's look at how this relates to the seismic observations that were mentioned a little bit earlier, with that 10 to 40% reduction in seismic wave speeds. So average mantle, that average mantle, average Earth diagram I showed in the beginning of the talk, gives the radial average seismic properties shown here in blue. And our measured P wave, so these are all the pressure waves, is more than 50% lower than average mantle material. So typical mantle materials fall in this box in this range up here. And now we can see the same drastic phenomena that happened in the shear wave in this material. And we see decrements of seismic reports of just how low they've observed seismic wave speeds. So if we look at these measurements, we see that these measurements were done without even heating the sample. So this is a solid phase that is characterized by extremely low vibrational properties. And if we heat this up, it probably will get even lower. So we only need probably a fraction of this material to explain the seismic observations. But is it dynamically stable? Recall the melt example where it's been difficult to contain the melt, or that it just pools around and forms a ubiquitous, very thin layer, which can't really be explained from seismic observations. So PhD student Dan Bauer did geodynamic simulations including this iron-rich oxide as a distinct chemical layer. And with different proportions of that oxide, we get either bulbous-like or teepee-like shapes with perhaps some entrainment into the mantle, which means some of it escapes. Or if we put more of it in, let's say 10% or more, then we get what are more characterized as like pancake-like features. And from seismic observations, if we plot all the seismic observations with the thickness of the blob and the P wave reduction, so down to 20%, and we model that with a mixture of perovskite, the coexisting silicate, we see that these the seismic observations here can match well with some of these shapes and thicknesses of these blobs, and they're quite stable. So over geologic time, they can stabilize themselves, and they can then be probed by the seismic observation. So they're not transient features. They will likely not go away. And so that's a very interesting result, because we didn't expect that such low velocities for a solid material at pressures of the Coremantle Boundary. So these are extremely high pressures, 1.4 megabars, and it's still very, very soft material. And so we have a great match to the observables. So now let's move on to the next part of the planet. So how many people have seen the movie The Core? A few? Well, it's also science fiction. And they take an interesting journey into the core, where they're trying to reset the circulation of the outer core to protect planet Earth. And there are a lot of improbabilities in the movie, of course. It's science fiction, but we prefer to take the science faction route and study the iron alloys that are expected to be inside of the core. Now, the reason why this is important is because this boundary, there are several reasons, but for the purpose of our discussion on these low velocity zones and the dynamics in the mantle, is that the temperature of this boundary is really not well constrained. The error estimates are about 1,000, plus or minus 1,000 Kelvin, depending on current calculations and experiments. So what we would like to do is introduce a new way of determining melting and understanding how the material melts. And so we've taken a densely packed iron metal in the hexagonally close packing arrangement, and we've measured the vibrational properties. So all of these modes here characterize the vibrational states of this iron metal that's compressed all the way to 151 GPa. And this is now into the core pressure. So we're 1.5 megabars. The Coremantle Boundary is 1.4 megabars. And in these measurements, we're able to, simply by probing all the vibrational states, we obtain a thermal pressure, which will help us with the understanding how the material melts. And we can also determine the sound velocities. The focus will be on the melting point and how we use those vibrational properties to know an accurate melting point of an iron or an iron alloy. We have an infrared laser that is focused in line with the X-rays to the sample that's been squeezed inside the diamond anvil cell. And we have a detector out here that detects the signal. And in our lab, we also have a laser heating system that we're able to at least test the sample configurations and do phase relation studies in the future. So here is the iron metal foil that's inside the sample chamber. It's only about 90 microns wide in diameter, so that's about 0.09 millimeters. So very tiny. And what we do is we heat this sample, and at the same time, each time that we heat it, we measure a temperature, an emission temperature, and we also measure the vibrational properties. So this quantity here is the total averaged vibrational properties of the iron metal. And we do that with increasing the laser power. So here's a video of what that iron foil looks like. All the lights have to be off because we have to use a spectrometer that's sensitive to measure that emission temperature. So this is the iron foil coupling to that infrared laser. And at each step, we measure the total intensity under these curves, so at low temperature and at higher temperatures, until we cannot detect a signal or an observable signal that's within the noise of 0. And this is where the material melts. So what we have done here is that we have just measured a melting point of the iron metal using a new method. So this particular method hasn't been used before. And we also have a tracking of the vibrational properties. And so this is something that we're developing right now. So this is very new. And we're able to determine the pressure accurately because of those vibrational measurements that I just showed here. This is able to tell us accurately what the thermal pressure of the whole system is at these high temperatures. So going back to complete the circle of, say if we want to call that the convection circle, we've sampled material down at the Coremantle Boundary. We've shown how we're constraining the temperature of this thermal boundary layer. But now you may ask, what happens to the material if it gets, or can it get too hot that it rises? And that may provide us with a link to how these very large volume igneous eruptions have occurred in the past or could occur in the future. And so understanding not only how materials behave at these pressures and temperatures, part of that understanding is the density of the material, or the volume. How does the volume change with pressure? And so if we take, so here, buoyancy of materials, we want to ask that question, how will will this material rise? Will any material rise? Especially if it's dense. So we've measured the volume. This is one of those features that we observed that was not observed about 10 years ago. As we increase the pressure, we see a deviation from this dashed line, which was thought to be how this material behaved about 10 or 20 years ago. So in this vicinity, the material, which is this iron-bearing oxide, that those iron atoms that are sitting in the lattice, they undergo what's called a spin crossover. Their spins in their outer D shell become paired at high pressure. And in that process, it undergoes a volume collapse. So that makes it a lot denser than what we would have thought originally. So how does that density change with pressure and temperature due to this transition? It's in fact a very broad transition. This colored map shows the red are all of the iron states in this very buoyant case. It's a high spin, it's very buoyant, compared to its low spin counterpart, which is the area all in blue. But then as soon as we follow a mantle temperature profile, which are depicted in these different lines here, we see that it samples a region where the crossover is characterized as a broad crossover. That's why it's in fact not called a transition. And so how does that affect the dynamics? Well, here is a geodynamic simulation that Dan Bauer has worked on to incorporate this spin crossover. And the interesting conclusion that came away was that it's effectively adds convection vigor to the system. So it increases the convection vigor, which means that the advective heat transport is more effective. You can imagine this is a more rapid stirring of the mantle, and which also would lead to a reduction of temperatures at the Coremantle boundary, because over, let's say, a fixed amount of time, if we compare it to a case where we didn't introduce this interesting crossover behavior. So there is an increased buoyancy that is delivered to the mantle simply due to this phenomenon. And if we measure the wave velocities, we see that they are also anomalous. So if we look at these lines here, that describes normal material, generally increases with increasing pressure. And this is work that postdoc Bin Chen is working on. But as soon as we add iron into the system, which they're indicated by these numbers, or the amount of iron in the oxide, we see that it increases first and then decreases, and then increases again. And this region right here is due to that spin crossover. Those outer D electrons are pairing and causing this behavior that wouldn't have been predicted if we stopped, which had happened about 10 years ago at about 20 or 30 GPa. So if we combine in a general sense what different compositions are appearing to be characterized by, this is simply just the state of what we know so far, and it's also still inferring quite a bit. If we take regular basalt, that can be characterized by higher P waves, higher density, or rho, and Prem is that average Earth, so this is just regular mantle. This kind of gives us a guide as to if we have a seismic observation and we see an increase or a decrease in wave velocities, what composition is that going to be? And we can take these deviations and compare those to seismic observations, and then take the density variations and put them into dynamic models, which we show here as a 4D model tracking plate tectonics over 200 million years and taking snapshots at 80 million years to the present. And this is a structure underneath the Southern Pacific, which is evolving over time, which takes into consideration these density anomalies associated with the composition that we inferred seismically and from the experiments. So this can help us aid in the link between buoyant material from the Coremantle Boundary and perhaps the long-term evolution of this volume and whether or not it will eventually rise up to the surface. So in conclusions, I want to simply conclude with the emphasis on understanding the vibrational properties of minerals and how important they are and how exciting they are in our understanding of the Earth's interior and also other planetary interiors. Now, the Earth offers us a very unique laboratory because we do have seismic observations, and we have, so that therefore we have the ability to illuminate the interior of the Earth. And that also helps us then to make predictions about what will happen in the future. And these observations that we made, combined with the geodynamic simulations, they help us understand the plume behavior. And in general, the complexities in Earth's deep interior are intimately linked to the events that occur near Earth's surface. So with that, I'd like to thank you. I'll take any questions.